So today we are learning about some periodic trends. Now, there's a very particular reason why we call this thing over here the periodic table. What does it mean for something to happen periodically? Yeah, over time, again and again, repeats, right? And that's the way this thing is structured, is there are patterns throughout that continue to repeat themselves. Now, we're going to learn 5 different patterns today, and then we'll learn more later on in the year. But all the patterns, all of the reasoning goes back to Coulomb's law, okay? And the more you can link it to this, the simpler this topic becomes. Because then rather than memorizing 5 different patterns, it's really just one. Okay, so try to find this common theme. So we actually introduced this to you last time, but Coulomb's law is that idea of positive and negative forces. Okay, that positives are attracted to negatives, and it's affected by the charge, or the magnitude of it, right? The more protons something has, the stronger the magnitude, and the distance. The closer the magnets come, the stronger they hold. Okay, so think in today's lesson, think about little magnets, positive and negative things. Okay, here's kind of some graphs. We looked at these last time, right, with our little quiz. The farther away something is, the lower the force of attraction. And the more positive something has, the stronger the force of attraction. So magnitude and distance are the 2 main things that affect positive and negative forces. Now, I need you all, if it's not, and I know it can be tricky 3rd period and we're going back to back, but I need you all to turn your brains on, because what I'm going to ask in today's lesson is I'm going to ask you to come up with a hypothesis of the why before I just tell it to you. Being that there's a lot of power in forcing your brain to try to make a connection, even if it's not all the way right, rather than you just regurgitating what I say, okay? But I can't get inside your brain and force you to think, is what I'm saying. As much as I wish I could, I can't do that. So you've got to do it yourself and not just sit there thinking about lunch or something else, okay? Okay, so now as we're talking about these forces, there's a few things we got to take in mind, okay? So the electrons are all attracted to the nucleus because it's positive. How do electrons feel about each other, though? They repel, right? So there's a lot of pushing and pulling happening at the same time. Primarily, especially when you start thinking of the inner ones versus the outer ones, right? These outer ones kind of get, the word we use is shielded from the nucleus a little bit because of all these inner ones spinning around, right? They block that magnetic force from them feeling it as strongly. Once again, that's why with our photospectrums, that's why the inner ones, right, have so much stronger of a binding energy than the outer ones. It's not only the distance, but they're also not being shielded from anything. Okay, so that's kind of what our picture here is showing. So this idea is these ones shield the outer ones from feeling the force of the nucleus. Now the name that we give this force is known as the effective nuclear charge. Okay, effective nuclear charge is the net positive charge experienced by the electrons in a many electron atom. In a sense, this is the strength of the nucleus. The stronger the effective charge, the stronger the hold. If it has a low effective charge, then it's not as strong. We abbreviate this as Z with a little EFF as a subscript. So I often, when I'm talking, I'll call it Zeph. Z-E-F-F. Okay, Zeph. Zeph is the strength of the nucleus. The stronger the Zeph, the tighter it holds. Other direct link is the more protons something has, the higher the Zeph is going to be, because, once again, more protons, more positive strength, okay? Okay, first trend, atomic radius. Now, when we use the word radius here, it's the same idea as the radius of a circle, which is half the diameter, right? So the radius of an atom is literally measuring from the nucleus to the outside edge. Or in a sense, it tells us the size of an atom. Literally, scientists have measured, even though they're teeny, 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 tiny, they have measured how big atoms are and given them a measurement. They're normally measured in a value called a picometer because they're so small. A pico is, 10.
How do they measure that?
Crazy, huh? I don't know how to simply explain it. Let me think, Taylor, and I'll get back to you. I know, like a little tiny ruler.
Just like
yeah. I don't know how to explain it simple. I'll get back to you on how they measure it. But it's crazy because they can. So you can literally look up measurements of how big is hydrogen, how big is lithium. The thing about AP, though, is it's not about we're not going to memorize any values here. We just want to know what the pattern is because then you can predict unknowns. So let's start. We're going to always look left and right on the periodic table, and then we're going to look up and down. Okay, so starting left to right, so as I go from the left side of the table to the right side of the table, I want you to make a prediction. Okay, do atoms get bigger in size or smaller in size when I go from left to right? So just make a prediction in your head. I guess the blank here would be increase or decrease. Tends to bigger from left to right. Okay, make a prediction. Now turn to your table buddy or group and tell them your prediction and why you said that. Ready, go. Thank you for your conversations, and if you're ever wrong, it's not bad, remember, it's good. It's good to be wrong rather than to be nothing, okay? That was a bad sentence, but you get what I'm saying, right? I'll make a fortune cookie out of that, okay? But atomic radius actually decreases from left to right. So atoms get smaller, or let's compare to neon is smaller in size than lithium. Now keep in mind, we're talking size here, not mass. Neon is heavier, it does have more things, but why are they getting smaller in size, Evan?
Is it because the protons are pulling everything in?
Exactly, right? If you think of lithium, so lithium has 2 rings, neon has 2 rings, okay? I should pretend this is neon because I drew it smaller. Okay? But what's changing about them? More protons. So this one has 10 protons. This one has 3 protons. Okay? This one has 1 electron on the outside that's being pulled. This one has 8. And so that stronger magnet in the middle literally shrinks that second ring a little bit. It's not a drastic difference, but it is actually smaller because of that strong nuclear force. Evan, have a smiley face for sharing with us. Questions on that? Taylor, why do you seem uneasy about this?
Well, I'm just the pictures don't make a lot of sense. Because one of them has 3 rings.
Oh, I didn't draw a ring. Better?
All right, there we go.
Okay, it was just my picture. Phew. Okay, I thought there was a bigger problem. That's an easy fix. Okay, any questions? Okay, side note 2, I'm never going to write the Y on the board because I want you to put it into your own words based off our discussion of it. If you're a paranoid note-taking person, you're no, but I need it really, really accurate, there's a big box right below or on the next page that gives it in a very detailed AP style way. Okay, so in case you're but I need to hear it in technical terms. I'll show you that and it's already in your notes. But I want you to write it into the Y so we can get better at explaining our answers. So I'll give you a second, fill in the Y. And then we'll make a prediction for the other direction. Hey, you're good.
Oh, okay.
I haven't gotten that thing to work yet.
Most teachers don't, but I never know if I should assume they don't
Yeah.
or assume they do.
Yeah. Okay, everyone ready to make their next prediction? Okay, make a prediction. So now we're looking top to bottom. Still talking about size. Does it increase or decrease as I go from down, top to bottom? Write down your answer and then turn to your table buddy and tell them what you think.
Yeah, well, they're
Atomic radius increases as I go top to bottom. Anyone by raising hand have a theory of why? Yeah.
Because it adds more outer shells.
Okay, perfect, simple. But what Zach said is totally true, right? So as I go down, let's come over here. If I'm comparing lithium to sodium, it is important to note, does sodium have a higher nuclear charge?
Yes.
Yeah, it has 11 protons when this one only has 11.
3.
What did I just say? 11.
That's 11. This one.
I said 11 twice. Okay, erase. This one has 11, that one has 3. But you're adding on, right, an entire new ring of electrons, right? An entire new energy level. So what's interesting is that actually there's a much bigger change going down than going sideways. This change isn't that much because we're just shrinking the ring we already have. But when you're going up and down, you add an entire new energy level, which even though this is pulling harder, they're just farther away, right? No matter what. So, very good. Zach, have a smiley face for that. Questions on that one? About why? Once again, connecting it back to Coulombic attraction, it's always about either magnitude or distance. In this case, the distance just gets bigger because you have another energy level. This way, it's all about the magnitude. The magnitude is stronger, so it pulls it in tighter. After you answer your why, go ahead and try this practice problem. Maybe, where'd my mouse go? There you are. Try this practice problem with your table buddy. Ready, set, go. Okay, give me a pencil drop when you're done. Did I just draw on my mask? Okay, I felt myself like touch my face with my marker. Okay, everyone ready? I think I just see some people working on their justifications, which is awesome. Okay, if you got this right, you can have a smiley face. What are we doing? Big to small or small to big? Small to big? So the smallest would be carbon. And then boron. And then silicon. And then aluminum. Have a smiley face if you got that right. Any questions on that order? Okay, now once again, just kind of showing the periodic table, the general trend is this diagonal up to that corner, right? Helium is the smallest atom on the entire periodic table. Francium is the largest. Up and down, though, changes a lot more than left to right does, which is why the two on the top row are smaller than the two on the row below, right? That's why boron got placed before silicon. It's because when you go down, it's going to get bigger. So, Taylor, do you have a question?
Does like the size of an atom, like electron-wise, affect its half-life more, or like the amount of protons there is?
Half-life in terms of like that type of stuff actually is just about the nucleus. So electrons play no role in radioactivity. It's actually about proton to neutron ratio. That the elements that are radioactive and have a half-life, it's because of their neutron to proton ratio. So, good question. Max, did you have a question?
Sorry, what
You're good.
was explaining to me.
Oh.
I guess I'm still a little bit confused on like why an atom that weighs more and has more protons would be like smaller than another.
Okay, yeah, no, let's clarify that. Great question. And keep in mind, so we're talking literally about the size of it, right? Like the actual distance from the middle to the outside. In terms of, go ahead.
Okay, that makes a little bit more sense. But
So it's like your height, not your weight. Okay? Where like with the atoms, yes, neon is heavier than fluorine. But size-wise, neon is shorter because its nucleus pulls on the electrons, so it brings them in tighter. Does that make sense?
Yes, that does make sense.
Great question, because it is important to distinguish between those two and not get mixed up with like mass versus atomic radius. So, any other questions? Yeah, Kimberly.
Can you just explain one more time, like why carbon is smaller than boron?
Yeah, so carbon would be smaller than boron because they're on the same row, meaning they have the same number of orbitals. But since carbon has one more proton than boron does, it can pull on that second orbital. It pulls on that second orbital stronger, and so it decreases the size of it a little bit. And it's not much. Like, let me pull up my list of the actual numbers. So boron has an atomic radius of 83 picometers, and carbon is 77. So it's like very, very small, right? Versus aluminum is 143, right? So very big jump. But yeah, left to right, like if you look at the actual numbers, like even like oxygen is 73, fluorine is 71. So it's like a neon is 70. So the difference between fluorine and neon is 1 picometer. So not much because it's just shrinking it in as much as it can. But yeah, great question. You're good? Okay. Any other questions on radius? Okay, so then this. Okay, I'm not going to read through these. These are spaced throughout. But this gives you an idea in terms of AP. If you have to justify something, what will get you points and what won't get you points. Okay, so this is a great thing to kind of like look over in terms of like if what you wrote as an explanation would actually count. The biggest thing to recognize is the biggest things with the don'ts is you can't just state the pattern. Your justification can't be, oh, carbon is smaller than boron because it's to the right. That's not an explanation, that's just a pattern, right? You have to get down to what's causing that effect, right? In terms of left to right, it's our nuclear charge or our Zeph. And I highly recommend using this word in your explanation when you're going left to right, because then it just really clarifies to the grader what you're talking about. And then up and down, it's all about those energy levels, right? The energy levels increase, get farther away. So, okay, next trend. When atoms become an ion. Okay, so let's write down 2 definitions really quick and then we'll talk about this. Can you see, I forget, I moved my little markers. Can you see my hand if I write right here on the screen? Yeah, okay. Okay, so we have something known as a cation and anions. Okay? And yeah, you say it as cation, even though it kind of looks like cation. And this one you say anion, not anion. Okay? But a cation is a positive ion. And an anion is a negative ion. Dumb chemistry joke, but you could remember that cats have paws, and that's why cations are positive. I told you it was dumb, okay? Anion sounds like anion, which sounds like onion, which make you cry, so they're negative. A little bit of a stretch, but yeah, a little bit stretch, but you know. Okay, so what happens to an atom that makes it become positively charged?
Take an electron.
Good. So cations are formed by losing electrons. Okay, and then obviously the reverse, formed by gaining electrons. So the pattern we're looking at here is understanding the size change when something gains or loses electrons compared to its normal parent atom. So what this picture is showing us is everything that's gray was the neutral atom. The pink is the ion it turned into. So when rubidium loses an electron, it becomes positively charged and decreases in size by a decent amount, right? So there are numbers right there. So why would rubidium get smaller when it loses an electron, Claire?
Because there's less electrons to pull in, so it gets lighter.
Perfect, good. And look, let's take it a step further. Look at rubidium on the periodic table. If I take away 1 electron from rubidium, I lose a shell as well, right? Which is why it's such a big drop. Because we are losing that electron, and so there's less to pull on, and that entire outside shell is gone. Good. Have a smiley face for that, Claire. Verse side, anions. So this is the parent one. This is neutral. When it gains electrons, it gets bigger in size. So why are they going to get bigger when we add more electrons in, Matt?
Because there's less protons than electrons.
Yeah, so number 1, there's less, the protons are the same, right?
Yeah.
But there's more electrons than protons, like you've seen. And so there's more that they're having to pull on. Good. Other ways we could put that? Have a smiley face for that, Matt. How do electrons feel about each other?
They don't like it push away.
Yeah, right? If I throw another electron onto this ring, they all start pushing more, and so the ring has to get bigger. Right? It's kind of like I imagine them like they're playing like Ring Around the Rosies with each other, and someone else wants to join the game, so they have to spread out, especially because they don't really like each other anyways. So, very good. Questions on that one? Okay, let's check it with this practice problem. Try this with your table buddy. Ready, set, go.
But absolutely all yeah, so it's also plus 2, right?
Yeah.
Oh wait, no, never mind.
Give me a pencil drop when you're done. Okay, everyone good? All right, let's check it. So first thing, this is my logic. So I'm ranking these three. So the first thing I'd say is, well, let's compare calcium and magnesium just in general. So if I look at the periodic table, they are right here. So for size-wise, going down is going to make it bigger. So I know right away that magnesium 2+ is the smallest either way, because it's a row above the other two. Okay, so what are we doing? Order big to small? Small to big? No, big to small. So that should be... Okay, so I know that this one's the smallest. Then I just say, all right, well, cations are smaller than the atom itself, so there's my order. Have a smiley face if you got that order as well. Any questions on that pattern? Okay, trend number 3. Oh, once again, there's your explanations. You can read through of good and do and don't do's. Okay? All right, ionization energy. Ionization energy, by definition, is the minimum energy required to remove an electron from the ground state of an atom. So it's very similar to what we were talking about with photoelectron spectroscopy of removing their electrons. Ionization energy is the energy value. The way I think of it is, how much do I have to pay this atom to get an electron? Okay, the more I pay, the harder it is to obviously get that electron off. So let's have you make a prediction. As I go from the left side of the table to the right side of the table, do you think ionization energy increases or decreases? So think in your head for a second. You can write it down if you want. Turn to your table buddy and tell them what you think. Ready, set, go. Okay, take your finger, keep it underneath your chin so other people can't see, and just point up if you're voting it's increasing, point down if you think it decreases. I just want to see your thoughts before I tell you the answer. No judgments here. So as I go left to right, ionization does increase. Very good. Okay, Jeff, I'm going to pick on you because I heard your answer. Oh, boxes. You're welcome. Thank you very much. Okay, sorry, coming back here, right? Close your mouth. Jeff is going to explain his logic of why it increases. Go.
So it increases because there's more protons that
Beautiful. Great answer. Exactly why, right? The more new protons something has, that stronger that nuclear force, and the stronger this magnet, the harder it's going to be to pull it off, right? Or the more it's going to cost to get it ripped off. Taylor.
Could it also be that like the ones to the left want to like drop a shell, whereas the ones to the right want to gain a shell, or like make a full shell, whereas like having an empty shell.
Kind of. It's like part of the stability, but it's not the reason.
Okay.
It's kind of like, I don't know in math if you guys have done proofs or not, but it's kind of like a one-way thing. Like, it's connected, but it's not the exact reason.
Mm-hmm.
But you are totally right. Like, the noble gases are very resistant to losing an electron because they have that full shell.
Mm-hmm.
But that doesn't exactly play into the energy part because it's all about the positive and negative forces. But yes, that is definitely a pattern that's connected to it as well. So yeah, good connection. Okay, make a prediction up and down. Okay, as I go down the periodic table, do you think ionization energy will increase or decrease? Make a prediction. Turn to your table buddy and tell them what you think. Go.
I think it's like how you said earlier, how when there's more shallows, it's I think that as it cells are added, it gets further away, so it's easier to
It's hard. The reason why it takes any energy is as you go to the right, what happens to the nucleus? Yes, another great question. The size actually can produce it too, right? The smaller one can hold up tighter. You are, that's a great point though, you're totally right. Francium has a very strong nucleus, but when you're talking about removing the furthest electron, it's so far away. What's that?
What's the ground state? Is that just like the outer shell?
That just means they're in the lowest possible state. So it's like the normal configuration.
Okay.
So,
So when you're moving electrons, is it like moving all the electrons or just moving?
oh, good question. So we'll get to that actually in a second of where you can label things as a first ionization or a second ionization. Generally speaking, if we just use the term ionization energy, it's normally referring to the first, meaning one electron. But you can have a second ionization energy, which means you're removing two and so on and so forth. Does that answer your question? No, good clarification. Okay, show me with your finger again your vote. Does ionization energy go up or down? Very good, it does decrease. Okay, Winston, I'm going to pick on you because you had a great light bulb moment. So why does it decrease as we go down a group?
because the electrons are getting really far away from the protons, and it just can't hold it very well.
Yeah, right? Like if I'm francium, my valence electrons are like down the hallway. They just like fall off, right? Like they give them away so easily. So good, have a smiley face for that, Winston. Take a second, write down your why if you didn't. These whys, by the end of the lesson, should hopefully feel very repetitive. Because once again, all the trends go back to very common themes. Evan, did you have a question or comment?
So would that mean that like oxygen like +2, like with 2 like negative electrons, or like taking away 2 electrons,
Yeah.
is more rare than having like potassium -2?
Say that one more time. So you're
Or maybe not potassium, because that's the first one, but like would it be more rare to lose electrons for something that's higher up?
Oh,
than
yes.
lower down?
Yeah, yeah. And so this actually will directly connect to how they react, right? That the ones typically lower on the periodic table are more reactive than the ones above it. Same thing, the ones on the left are often very, very reactive because they're so willing to just give their electron to anyone who will take it. Yeah, no, great connection. So kind of building off of Zach's question in terms of ionization energy and like how many, we have these things. Oh, let's do this practice problem first, I guess. I forgot about it. Okay, do this practice problem at the bottom really quick, and then we'll talk about second ionization energies.
Yes.
Once again, give me a pencil drop when you're done.
Yes.
What are you increasing? Small to big?
Just sulfur, you know.
Yeah.
No.
Oh, I was like, wow.
The hardest one to be
Okay. All right, everyone, give me a little wave of your hand if you want another second to think yourself. Okay, I want you to be able to think yourself before I give you the answer. So I'll give you 30 more seconds. So here's how I go about like solving these sorting questions, right? Is I drew a little picture of a periodic table right there. But in a sense, that's kind of what I do with the one in front of me. Is I kind of figure, okay, first off, where are they all located? Okay. I then know that in terms of ionization energy, the ones that are furthest to the left and further down have the lowest. So automatically, I know that K has the lowest because it's the furthest to the left and further down than all the others. Then, these two are on the same row. Did I draw these not in a very good line? Thank you. Phosphorus. Okay? So those three are all in the same row, so now it's just a left to right trend. So it would go K, then NA, then P, then AR, And then questions on that? Yeah, Matt.
So on the graph on the side, it has like them decreasing with the energy or something.
This one?
Yeah.
So this one is interesting so it's graphing all the individual elements, right? And this shows the idea of why we call it a periodic table, is where we see a pattern of it goes up, it goes up, and then it goes back down. Because when I get to neon, I then go back to the left side of the table, and so then it drops down. So what we see is all of the minimums are on the left side, and all of the maximums are on the right side.
Well, like not the big jumps, like the weird.
Oh, yes. So that's the thing and why we don't memorize the trends either. There are always exceptions, right? That's the word we hate or strongly dislike in chemistry. So there's always exceptions to the general trends, right? And that's where you're not expected to memorize them. We're just going to go based off the pattern. You might be shown one, and you could have to provide a reason why. We'll talk about a few of those. But is that what you were saying, how it kind of goes like this? Yeah, great observation. Any other questions on that problem or comments? Okay, so with ionization energy, this is known as the first ionization energy. So let's write some equations here. So when I use the term first ionization energy, I'm referring to removing one electron. So let's pick aluminum here. Actually, we'll do magnesium. Okay, so the equation for ionization energy would look like this. Magnesium is going to lose, so that's the change, an electron. And by losing an electron, what happens to an atom?
It becomes positive.
Good, so then it turns into Mg+. This would be the equation for the first ionization energy of magnesium. We've lost one electron. Second ionization energy would mean you've already lost one, so you're already at a positive charge, and now we're going to pull off a second. So losing an electron and turning into Mg2+. And then so on and so forth. The third would be removing another one. Yeah?
So for like potassium, the first ionization energy would be easier than argon. Would the second one be harder?
Yeah, so it gets really interesting when you start bringing in, comparing like second to first, right? So let's build off with Zach's question. So for magnesium, these are actual values right here in energies. So the cost for the first one is 738. The cost of the second one is 1,451. The cost for the third electron, though, is that much. So Zach, you were kind of like connecting something. Why do you see why there's such a big jump? What's happening there?
Because the outer shells are super far apart, but then one inner is closer together.
Yeah, when we start separating, so these two electrons are part of the valence shell. That third electron is what we call a core electron. It's an inner shell. When you start trying to rip electrons off the inner shell, it's really, really hard to do so. So that's what this blue line right here is showing, is the jump from valence to core. Or in a sense, once the outer shell is empty, and now we're trying to empty an inner shell, which is closer to the nucleus. The nucleus, remember, doesn't change in strength, but you're losing electrons, which means it has less to pull on, so it gets really, really hard to do so. Did that answer your question, Zach?
Yeah.
Okay, great question. Have a smiley face for that. Good job, Nina. Give him a hand. Questions on this idea? Okay, I have a question. Tell me this. Which of the following would have the greatest second ionization energy? Try to do it without looking at the table above.
What?
Like, look at the periodic table, but not like the... No, not... By the end of the year, you'll just know. But yeah, don't look at the ionization. And everyone's like, wait, I have to just know where they are. One day, by the end of the year, you'll be amazed at how much you can memorize stuff at the table. Because you will look at it. Just give you a blank periodic table and see how much you know.
How you do like in this way? All three.
And the last one, first two rows.
First two rows you think you could do?
Maybe like.
I should try that.
Oh, I can probably get
How should I get?
Yeah, because in my first
Yeah. You lose. Wait, what?
yeah.
Like, there's that one that's language is really well.
That one we did, but not
All right, give me a pencil drop once you have an answer.
Like when you get too much more pain, it's so difficult. Everyone just like decided to stop making new elements or else like not possible to make new elements.
These ones are actually these are technically ones that aren't named on yours, but are on mine. Those are like two more. So they're pretty recent, yeah. Yeah, so no, it also. And those were pretty recent.
But it's not easier to get
And that is one of the big, like, questions of chemistry is that it is there a limit, right? Like, you know, like.
all of that sodium.
So that's like the whole big, like, thing of why they're making ones, is they're trying to find how if you can make them actually stable. All of them made are but there's a theory of this island of stability we have where we actually find that is stable and useful. And useful. And that's the one that just disappeared.
That would be like lighter. It would almost look up there if you look at holding the phosphorus or like neon. And it would just be, the phosphorus would be
So a
one.
lot of them, like, because all of these ones, like, some of them would be like really heavy metals. So it's like for building purposes, like that, and like building structures and, you know, like stuff like that.
Yeah, it just depends on how we make it too. Because calcium, where is this element?
Like, couldn't it be
Oh,
like
what
one
is
big
calcium?
amount?
Is it-
But it would be something.
Where?
Oh, this is why.
Because it's like, if you're going to this, it's where it's like, the left is easier than the right, it's more like this.
And yeah, these ones are
Because if I like, it was further to the left,
2012.
it's easier to get rid of.
And I take off 2012 that thing on the page.
Because.
You like searching forever.
Sulfur would be easier because it'd be further to the left. Calcium would be.
Interesting, huh? That one always perplexes me too, that we have never found it naturally. But it seems like it should have been here at some point, right? He's saying 43. Technetium. It's interesting because, like, we've made it, but it seems like it should be an element that exists naturally, right? Why we can't find it, I don't know. The one they made, I don't think so. Most ones we make are just stable.
like, so for calcium, you'd be.
Yeah, kind of interesting, huh?
But then it would come in a different place, so it doesn't take as much space, but it's still like, this is the and this is off the one.
And that's what he did, I just have a really good. So, it does come up with another half life.
And you're shown. And it's like,
Yeah, it also gives you, that was the interesting element.
so then, so much.
Okay, on the count of 3, you're going to shout out the name of the element you pick. Ready? 1, 2, 3. Sodium. You pick sodium, you're right. So I show me wrong together. So, I think, oh yeah, you can have my face if you want. A little shortcut, everybody, with valence electrons that I don't think we've talked about yet. Okay, to determine how many valence electrons something has, and I mean, pretty much they're just looking at a table. But the biggest thing to remember is that this D block, those don't count towards the valence shell because it goes 4s, 3d, right? So for valence, everything in this column has 1. These all have 2. And then it goes 3, 4, 5, 6, 7, 8. Determining valence of this middle group, how many would they generally have?
A lot.
If all the electrons in here don't count, how many valence do they typically have? 2. Because they only have the 4s that comes before it. Now, it gets a little weird, though, because this section is where all of our exceptions to the rules also happen. So sometimes the electrons are like jumping. Pretty much what I'm saying, though, is you don't need to know how many they have because it varies. But generally speaking, a lot of them actually have 2 or close to that. So, okay. Questions so far? Okay, we got 2 more trends. Here we go. Okay, next trend is known as electron affinity. Now, electron affinity is opposite in definition to ionization energy. It's not opposite in numerical value, but it is opposite in definition. Meaning, if ionization energy is the energy it takes to remove, affinity is to add. Okay? Now, we need to understand with energy, does anyone know from physics or other classes, what does a negative energy mean? Anyone know? It's okay if we don't, I just wasn't sure.
It gave you energy.
It's a direction. Yeah. So it's kind of like having a negative bank account. Is there any such thing as negative money? No. But if you have a negative bank account, where's your money going? Out or into the bank? Out. So negative energy means it's coming out of the atom. Or in a sense, the atom is paying me with energy when I give it an electron. Positive energy means it's going in, or I have to pay the atom to take this electron. So affinity is a little weird because of this negative idea, but the more negative the affinity, the more willing it is to take that electron, because in a sense it's paying you when you give it. And the more it pays me, the happier it is. So fluorine is really happy when I give it an electron, so it pays me a lot of energy. Neon doesn't want an electron. I have to pay it to take an electron. Yeah, Zach?
Why do all the ones above 0 don't have like a certain number?
A value? That's a great question, actually. I don't know. My guess is maybe that they can't measure it because it's so hard to actually make it happen. Because these other ones are actually like measured values. They measured how much energy comes out. So I don't know if the other ones, I'll have to look and see, or if it's just this table and it just wasn't putting a number to it. I'll look and see if there are actual numbers to it, but this is just showing the pattern. Great question. Matt?
What is the numbers like?
So it's a measurement of kilojoules, so it's energy. And they just measure, most of the time it's a form of heat. So like it releases heat is typically the form that we see. So does that make sense? Answer your question? Isaac?
Well, the numbers are just like the energy the atom has.
It's the energy the atom releases when you give it an electron. So in a sense, yes, it's coming out of the atom when it's given an electron. Now, if you notice more at the numbers, this is the most exception trend there is. There's a lot of variance of what's going on here, right? In terms of if you try to find a pattern. Generally speaking, as you go down the table, electron affinity, you got to be careful how you phrase it, but it decreases in terms of the negative value.
They don't pay you as much.
They don't pay you as much to get an electron, right? And generally speaking, as I go this way, they pay more for an electron, but you got to drop off the noble gases, right? And then nitrogen's also weird. Let's talk about nitrogen really quick. Any guesses of why nitrogen would be resistant to gaining?
Well, would it be because it's kind of stable because it has like that half fill?
Great, right, great connection. Have a smiley face, right? Configurations help explain why all these trends are happening, right? Nitrogen is that half-filled configuration. If we throw another one in, right, we get that repulsion, which disrupts it. Yeah?
Why doesn't that pattern like
Carry down? Yeah, I mean, we still see a drop, right? But it's just now because of sizing. Is the bigger something is, the farther away the electrons can be, even in the same orbital, right? So we draw all the boxes the same size, but in the actual atom, a 3p orbital has more space than a 2p orbital does. And so there's less electron to electron repulsion going on. So great observation. Kind of same thing here, right? We see what's happening here at the atomic level. Why do they not want another one? Yeah, they're at a full shell. We'd have to add the P, right? Yeah, Carly. The atom would release energy when it gains that electron. Does that make sense? Yeah, good clarification. Other questions on affinity? I'll be honest, this is the least, I probably should knock on wood or I'm going to jinx us. But this is the least likely trend you'll be asked about on the AB test.
It's not very true.
It's not very trendy. Yeah, most of the, I always see atomic radius, I always see ionization energy, and you always see electronegativity. But this one, pretty rare that it pops up. I want you to know what it is, but in terms of classifying, because it's so up and down, you wouldn't normally rank them like we did the other questions. What you could see is questions kind of like what Bryce answered is they give you data and then you answer questions about it. But okay, I'm not going to start electronegativity because I don't want to get halfway through. So we'll finish that up next time. Oh, darn it, it probably is actually. Okay, so for the homework, so do as much of the worksheet as you can that doesn't apply to electronegativity. Do the reading still, because then you'll get a preview of what electronegativity is. For the AP classroom, I will, you don't have to do it. Is there a way to start it and not finish it? I didn't put a timer on it. I mean, but so what I was thinking is you could at least start it just so you don't have as many quiz, because you'll have another quiz next time.
If you change the due date and then you don't make it timed,
So yeah, so I'll leave it open until next Wednesday. Wait, when? Yeah. Is that when I'll see you again?
Monday.
I mean, no. So normally it's going to close Monday, but I don't want it to close Monday. I'll change it so it doesn't close till Wednesday. So pretty much you can start this if you want, but you don't have to. So.